this morning will be Chris Leininger from the University of Illinois Chicago, who will talk about free-by-cyclic groups and trees.
Thank you. Thanks to the organizers. I'm from Urbana-Champaign, from Chicago. It says on there Chicago, but I'm from Chicago. Okay. So thanks to the organizers. Thanks to the people I was out with last night for not letting me stay out too late. So I want to talk about BNS invariant. So let me start with just a general definition. So suppose G is a, let's say, a finitely presented group. Actually, let's say it has a finite KG1. Let's not really, you can relax this if you like. So what is the BNS invariant? So it's BNS, that's Beeri-Neumann-Strebel. So it's an open subset, that's the theorem they prove. It's an open subset, call it sigma G. Usually you define it as an open subset of the sphere of directions in the first cohomology, but let me just take the cone on what they normally call the BNS invariant. So this will be an open subset of H1 of G. So I'm going to think about that as homomorphisms from G to R. And so it's a cone, so it's invariant under positive scaling. And so there's an algebraic definition, but I don't want to give that. Instead, I want to think about it geometrically. So what is how do you think about the BNS invariant geometrically? One way to do it is in terms of closed one forms. So what's a closed one form on X? Well, if X was a smooth manifold, then you would know what a closed one form is, and Durham cohomology allows me to identify elements of H1 of G as closed differential one forms. But so what does it mean for a closed one form, or for a one form to be closed? It means that it's locally d of a function. And so we can describe closed one forms just basically as locally d of a function, or just think about the locally defined functions. Or if you like, instead of thinking about them as being locally defined, go to the cover where they're globally defined. And that's the universal abelian torsion-free cover. So let me write x hat over x, the universal torsion-free abelian cover. So that's the cover corresponding to the kernel of the map from G to the abelianization of G mod torsion, which we'll just call H from now on. So H is the universal torsion-free abelianization. So if you like, this is isomorphic to Z to the B, where B is the first Betti number of G. Okay, so if I have a closed one form on a manifold and I go to the correspondent to this cover, then I can pull that closed one form back, and then it's globally d of a function. So let me just think about that. So let's take, so what's my closed one form? It's a function. We call it omega u from this cover to R. And then it should be equivariant with respect to u. So that is, if I take omega u and I take some element of H, so H is the covering group here. Take some element H and apply it to X. So that should be the same thing as if I were just to apply this function to X, and then add u of H. So why is this the right thing? Let me just draw a picture. So maybe here's x hat, and we have a function to R. So if I have some point how do I get from x to hx? Well, I think about lifting a loop. I take a loop downstairs, gamma, that represents h in h. So gamma is some loop. I lift it to a path. And then I think about integrating my one form along this path. And the difference between the value here and here should be the value of u on that path, so that's u on h. So the difference between these two is exactly u of h. Okay?
Sorry, what's u in the first place?
Sorry, u is a just any. Thank you. U is an element of. So for all u and h1 of x, I'm going to take some function that represents the class. Thanks. Okay, so now that you can represent, or now you represent your cohomology class with this one form, what does it mean for u to be in the BNS invariant? So the BNS invariant, it's the set of u in h1 of x such that if I take omega u inverse of 0 infinity, so I'm going to pull back the preimage of 0 infinity. So here. So I'm going to pull that back. I get something like this. The inclusion of this to x hat is surjective on pi 1. Okay, so that's the BNS invariant. They're the set of cohomology classes such that the positive part of x hat surjects on pi 1. Okay. So this is independent of all the choices made. It's independent of x. It's independent of this function, omega u. So you take any function that satisfies this condition. Maybe there's multiple components here. So really there's an unbounded component. So what we're really talking about it should be surjective on pi 1 from the unbounded component of this to x hat. Okay? All right. So I'll give you some examples, maybe something slightly more concrete. In fact, why don't I go ahead and just now restrict to the situation I'm interested in is when G is a free-by-cyclic group. Suppose G is free-by-cyclic. So finitely generated free-by-cyclic. So we've already seen this several times. So let me just remind you what this means. So G looks like, so there's a homomorphism. Let's call it U naught from G to Z. And an outer automorphism, call it phi U, maybe phi U naught. This will be sort of like the maybe the starting object. So let's call it phi naught. This is an element of out of the kernel of U naught. So the kernel of U naught, this is going to be a finitely generated free-by-cyclic group. The kernel of U naught should be a finite rank free group. And G looks like this free group, semi-direct product Z, using phi naught. Okay. And so this homomorphism to Z, the natural homomorphism that you get by taking the quotient by Fn, that's the homomorphism U naught. Okay? So in a minute, I'll explain why U naught is a point in the BNS invariant. But more generally, maybe just let me just say what happens. What are the integral elements in the BNS invariant look like? So let's say sigma z of G. Those are those elements U and H1 of G. Let me say, sorry, U in the BNS invariant, such that the image of G is exactly the integers. So these are the homomorphisms to R that land exactly on Z and live in the BNS invariant. Okay, so these have a nice description So from the work of Thierry Neumann-Strevel plus Gagin, Halleck, here, Wise. Being in here is exactly saying that, so for all u inside of this set, so these homomorphisms to z give you a nice decomposition of G, like these semi-direct products, but more generally, they should be ascending H and N extensions of free groups. So for each one of these, the kernel is free. Inside of the kernel, there's a finitely generated subgroup. Well, let me say it this way. First, there's an automorphism, so there exists phi sub u, an outer automorphism of this kernel. There's a finitely generated subgroup, QU, so a finitely generated subgroup inside of the kernel. So this is finitely generated. It's taken into itself by phi u. And then we can write G as an ascending H and extension over QU using phi u. So G looks like QU, an ascending H and extension with the restriction of phi u to QU.
Yeah, in general, kernel of U is only locally free. It's not free. It becomes free when both U and its minus are in the BNS invariant.
Sorry, thank you. Yeah, so the kernel of U is, locally free, thank you. Locally free. Yeah, so the next thing is what you just said, so if not only is U in there, but it's negative, so if U is in the BNS invariant, drawing the chalk, so if U is in the BNS invariant and its negative is in the BNS invariant, then this QU is actually equal to the kernel of U, and G is a semi-direct product. It looks like the kernel of U, VU, Z. Okay. Okay. So let me. So these are the groups that we're interested in. They're free-by-cyclic groups. I want to talk about the BNS invariant for these free-by-cyclic groups. And the case where things are the most interesting is when you're in some kind of an analog of a hyperbolic 3-manifold. So a lot of motivation for what happens for free-by-cyclic groups comes from looking at hyperbolic 3-manifolds, fibered hyperbolic 3-manifolds, and trying to sort of push the structure from fibered hyperbolic 3-manifolds over to these free-by-cyclic groups, and that happens. That analogy is most useful, or maybe is strongest when you assume a little bit more about phi naught. So let me make that assumption. Let's suppose that phi naught is atoroidal and fully irreducible. Suppose phi naught is atoroidal and fully irreducible. So atoroidal means, according to a theorem of Brinkman, so Yael mentioned this in her talk, so this means that G is delta hyperbolic. So that's the atoroidal assumption. There's no Z plus Z subgroups, and indeed the G is a Gromov hyperbolic group. The full irreducibility is a dynamical property it's an algebraic property, but it has dynamical implications. So in particular, there exists a train track, an expanding irreducible train track representative of phi naught. So let me, so what does that mean? That means there's a graph. So gamma is a graph. We have a map F from gamma to gamma. I've got an identification of pi 1 of gamma with my free group. And F star, with respect to this identification, is equal to phi naught. So that's just a topological representative. So that's what I mean. I'm going to represent this automorphism geometrically or topologically. But then there's this expanding irreducible train track condition. And what this means, I think Echo mentioned it, what this means is that if I take F and I restrict it to any edge, so for all edges E, and then I iterate this restriction, this is locally injective for all edges E and for all n bigger than 0. So that means just that if I look at, when I apply the map F to this edge, so it goes to some edge path, and there's no backtracking. And then if I apply it again, it goes to some longer edge path, and there's still no backtracking. Apply it again, and again, and again. So that's the train track condition. Being expanding and irreducible just means that it's sort of every edge goes everywhere. So every edge eventually covers every edge. Meaning I iterate and iterate, and eventually actually the image of every edge is going to be the entire graph. Okay, so let me give you an example of such a map. This is my favorite example. So let me take, this is my graph gamma. Let me label the edges A, B, and C. Oh, sorry, C and D. And now, how can I describe a graph map? I can do this combinatorially by subdividing this graph. So I'm going to relabel the edges. I'm going to subdivide and relabel. So this is D, this is A, this is B, this is A, and this is B, A, D, B, A, C, and the directions go like this. Okay, so how do I get a map from this graph to itself? Well, I just send each one of these edges with the label to the corresponding edge over here with the label. And it might seem like this is a hard condition at first to check. How do you know that under all iterations you are locally injective? Well, the point is that there's sort of a last time. If it fails to be locally injective, there's sort of a last time that you iterate at which it fails to be, or it's locally injective, and then after that it's not. And so you can, instead of thinking about like starting from the beginning, you can just go to that last time. That's some point on some edge where it fails to be locally injective. And so, so actually deciding whether or not there's a this map is locally injective is really a under all iterations on the edges. That's really a finite check. And so the existence of this train track is due to Besvina and Handel. EL. Okay. All right. So there's an example. How do I what do I do with this to study G? So let's build a finite KG1, namely the mapping torus. So let's let X be the mapping torus of F. So let me just draw a picture of that in our example. So we take the product of the graph with the interval, and we glue the top to the bottom by F. Okay, so that's the mapping torus. And let's see, what do I want to say about this? So there's some nice structure here. So there's a semi-flow on this mapping torus. Namely, just take the product flow, so just flowing in the second coordinate with constant speed, let's say. So that flow, or locally defined flow on the product, gives me a semi-flow, an action of R plus. So when I get to the top, I flow. When I get to the top, well, F glues the top to the bottom. I go somewhere else, and then I can continue to flow. I can't flow backwards because this map isn't injective. It's not a homeomorphism. So I can't flow backwards, but I can flow forward for all time. Okay. Now this space X has a natural map to the circle. Namely, just take the product. So X is the quotient of the product, the graph across the interval. Just map the product over to the interval. And then when I glue the top to the bottom, I'm gluing the top of the interval to the bottom. Well, if I glue the top to the bottom, that's just the circle. So I get a natural map to the circle that represents, let me call it omega u bar, to sort of suggest where I'm going. So there's a map to the circle that represents the, u naught, that represents our starting cohomology class. So where, I guess I erased it. No. So u naught is our starting cohomology class. So the induced map on pi 1, from pi 1 of x, which is G, to pi 1 of S1, which is Z, is just the homomorphism u naught. So omega u naught bar star is u naught. Okay, so I called it omega u naught bar because I'm going to lift this map now to the universal cover of S1 from the universal abelian cover of X. Let's call that, so we still call that X hat. I guess I can draw this here. So I've got the map to here. This is X hat. I can lift this map to R, R, the universal cover of S1. And this is exactly the kind of map to R that we needed in order to define the BNS invariant. And now it's clear, it should be clear, hopefully it's clear, that, so note, U naught is therefore in the BNS invariant. In fact, it's the integral BNS invariant. So why is that? Well, let's just think about this picture. So if I go to this cover, again, let me draw the picture. Notice that, so let me give this flow here a name psi. I can lift the flow, the semi-flow here, call it psi hat. And then if I look inside of the map from, if I look inside of x hat at the flow lines, well, the flow lines here map over to, they map over or locally injectively, right? These flow lines are just running around the circle. So over here, these flow lines, they map over to arcs. So the map x goes to psi hat t of x. So I take a point x and I flow for some time. And then I apply the map this is injective. This is an increasing function. Oops, sorry, t. So I pick a point and I flow, and then I apply the map omega u naught, and that map is increasing. So why does that tell me that I'm in the BNS invariant? So if I take the preimage of 0 infinity, so that's back here somewhere. Well, if I take any loop in the space at all, I can just flow that loop up until I land inside of the preimage of 0 infinity. Okay? So any loop flows into omega u naught inverse of 0 infinity. So in particular, the map on pi 1 is surjective. Okay? So actually, the only thing that was important here was that these flow lines map over injectively. So let me define the subset of H1. So let's let S inside of H1 be the set of, so it's a set of all these classes such that there exists omega u representing u, so that happens, so that for all x in x hat, the map T goes to omega u psi t hat of x is increasing. Okay? So if I ever have that, then I can apply this same argument, and I see that that S is inside of the BNS invariant. Okay? So the first theorem is that it's equal. So sorry, not equal. It's equal to a component. So S, so theorem. So all the theorems that I state will be joint with Dowdall and Kapovich. So S is a component of the BNS invariant. So it's a not only does it sit inside of there, but it's a full component. Okay. So yeah.
For a generic S like that one, how can we define the flow?
So right. So maybe let me just, because maybe it kind of got lost along the way. So whenever we have fully irreducible atoroidal automorphism, we build this mapping torus from a train track representative of that automorphism. Then we take the flow for that cohomology class. Yeah, so the one that comes from that fibration. And then we're saying that that component of the BNS invariant is this set of classes representable by these kinds of one forms where when you compose with the function, it's increasing. Okay.
The same as psi hat.
What's that?
Psi hat doesn't change, just omega u changes. Is that right?
So psi hat depends on all of the starting data. Yeah.
But not on u. Yeah.
But well, I mean, it was built from u. It was built from u. Sorry, from u naught. Sorry, from u naught. Yeah.
But not u. Right.
Yeah. Oh, I see. Yes. Sorry. U and
that
yes.
was my point.
Yes. Okay. Okay.
I got confused.
Okay. I got confused answering also. Okay. Yes. So actually, let me say something about the other integral classes. So let's say SC. So again, we've got our fixed u naught. We've got our fixed flow psi. We get this component let's take the integral points. Okay, and then also say that the integral points, well, if you think about what it means for this to be integral, so the function, so our homomorphism lands in z, and we can take the quotient of r by the image of z, and the function omega u descends to a function, so if I take omega u from x hat to the r, if we're in z, so for all u in here, omega u, this function descends to a function to the circle. And still, the flow lines here are mapping injectively here. And the fibers, so for all u in SZ, the fiber, omega u inverse, omega bar u inverse of a point, any point, let's call that gamma u inside of x, is a section of the flow, is a cross section of the semi-flow. And the first return map, call it f sub u, from gamma u to gamma u. The first return map is an expanding irreducible train track representative. Let me put representative in quotes of this monodromy phi u from qu to qu. So I need to put this in quotes because it's not true. I've learned that if you put things in quotes, you can say things that are false. So what do I mean by representative? Well, the problem here why this isn't actually representative is because the inclusion of gamma u into x may not be injective on pi 1. There's not much you can do about that. But the image of pi 1 of gamma u serves as the group qu that we need. And the first return map, fu, so its induced map on pi 1 descends to the map from qu to qu. It descends to this map phi u. And maybe doesn't seem so useful, except for the fact that this is still an expanding irreducible train track map. It has those properties that I described earlier. And in particular, whenever you have, I guess I didn't mention it, but whenever you have an expanding irreducible train track map, you have the stretch function that was mentioned a couple times. So there's the stretch function, so lambda of f sub u. And this is exactly equal to the growth rate of phi u. So even though it's not actually a representative, topological representative, you can still capture growth rate with this function. And actually there's a way of promoting this to an actual train track representative. So there's more there, but I don't want to say too much more about it. The point is, though, that all of the integral classes, so maybe let's go back to the example. So back to our example. Let me draw a picture of, so here's h1 of g for our example. It turns out that the BNS invariant is the complement of 3 rays. So it's this cone together with this cone together with this cone. U naught is right here. And then we have all the other integer classes. Every one of these other integer classes can be represented basically by a graph transverse to this flow, and the first return map represents the monodromy. Okay. There are other descriptions of, let me not write it, there are other descriptions of this cone S. So here I described it as all the cohomology classes that can be represented by these sort of flow regular one forms. But notice that if I look at my mapping torus, the fact that the map I started with F was this expanding irreducible train track tells me actually that I have lots and lots of closed orbits. So there are lots of closed orbits. In fact, there's a dense set of closed orbits in X. And this cone S is also described as all of the cohomology classes that evaluate positively on the closed orbits. So it's clear that you get one inclusion, right? Because all these functions are, have this monotonicity property. If I take a closed orbit and I lift it to x hat, well, that's going to map over, to some positive segment. So the value is going to be positive on the closed orbits. But in fact, that also characterizes this. So this is similar to work of Fried in the case of three manifolds, and more generally, certain types of flows. This kind of condition. And just like that, you could also find finitely many closed orbits so that you're in the cone S if and only if you're positive on those finitely many closed orbits. And from that, if you like, you can see that the cone is rationally defined. So it's a rational polyhedral cone. Okay, you're positive. You're saying you're greater than 0 on some collection of integral classes. So this is very much like, again, like the Thurston norm. Okay. Let's see. This stretch function. So maybe let me just say something about this fact that these first return maps are train track, also expanding irreducible train track maps. The point is that the train track property is inherited by the train track property for F. If you take an arc anywhere in here that's transverse to the flow and you start flowing, it'll always stay transverse to the flow, so it never folds. Okay, so that is a useful property. That's really where the train track property there comes from. And let me, so each one of these monodromies has some stretch factor. And just like in the three manifold case, those stretch factors all assemble into a single nice function on the cone S. So here's another theorem. So this was, so we proved this theorem, and then also Algam Kafir, Hironaka, and Rafi. So this theorem really comes from the sort of McMullen/Teichmuller polynomial. So what is it? This is the sort of assembling these stretch factors. So the theorem says there exists a real analytic convex function called H from S to R, such that for all u in this cone, and t bigger than 0, well, first of all, as you go to the boundary, let me just say, as u goes to the boundary of S, this function blows up. It's homogeneous. So, I mean, maybe these are not so interesting, but these other properties. So once you know the value at some point, you know it all along the ray. And then this function restricts to essentially the log of this function. So if u happens to be inside of SZ, then this function, h of u, is exactly log lambda of f sub u, which is also log lambda of phi sub u. And the point is that this is purely algebraic. It depends only on the cohomology class in G. So this stretch factor. So So what this function, so therefore, I mean, this function is uniquely determined by the values on the integral points together with these other properties. And so, because this depends only on the group in the cohomology class, you see that this function is really, it's independent of all the choices that we made. It's independent of the starting train track representative of the particular cohomology class. Okay. Any questions so far, now that we're almost done? All right. So I mentioned trees. So where do the trees come from? So Yael mentioned the trees. So let's let gamma naught tilde be the universal cover of our starting graph gamma. And so Besvina Fain and Levitt and Lustig construct this stable tree. So the stable tree turns out to be a quotient of the universal cover of the graph. So there's this quotient map, which basically, what does this map do? It says that if you take 2 points in the graph and you start, so you lift your map F to this cover, and you start iterating, if those 2 points eventually get very close together after appropriately scaling the metric, then they're going to be identified in T. Okay? So you can also say this, though, in terms of X. So if I take, so I can think of gamma naught tilde as sitting inside of X tilde, the universal cover of X. And then the first return map to our section gamma is F. So it's not surprising then that you can describe this tree as basically the quotient of flow lines of this. It's not quite, you have to take some closure and transitive closure, but it's basically the flow space of this. Okay? All right. So let me state the theorem, the new theorem. So it's in the case of, so if you forget about X tilde, then in fact this tree T admits a metric so that my free group acts by isometries, and the map F gives me a homothetty of T exactly by the stretch factor. So I'm dilating the tree exactly by lambda of F. So if you want to think about it another way, so the group G therefore acts on the tree T in such a way that the kernel, the free group, acts by isometries. Oh, the lightsaber means I have 5 minutes. So the group G acts on T, the kernel, the free group, acts by isometries, and the stable letter acts by homothety. Okay? So the theorem is that that particular metric on T, right, so you could put it, instead of starting with F, I could have started with any other integral class, and I could have built the same tree, okay? And I can also put a metric on it corresponding to that class. I get the same action of G, but now with the different metric, the new kernel is going to act by isometries, and the new stable letter is going to act by homothety. So the theorem is that all those metrics actually fit together in a nice way, similar to the way that the stretch factors fit together. So there exists a continuous function. So this function goes from the cone to metrics on the tree. So metrics on the tree T. So it's continuous with respect to some kind of a weak topology. So if I take an arc in the tree, the length of that arc is a continuous function of S. Such that So let me write this as, so the class U goes to the metric d sub u such that for all h and h, or sorry, g and g, for all g and g, if I take g and so how does g affect the metric? It's exactly by e to this function h. Let me write it and then explain. U of h du. Okay, so what is this saying? Not h. So what is this saying? This says that when I apply the map G, it changes the metric in some predictable way. Namely, it's a homothetty where I'm scaling exactly by essentially this function that we wrote down over here, raised to the value of u on the class G. So in the case where u was integral, for example, then this is exactly the metric that I was describing before. But now we're saying that these all assemble together. So maybe just in particular, if G happens to be in the kernel, then I'm not scaling by anything, I'm acting by isometries. So for all G in the kernel of U, G acts by isometries. Bless you. Okay. So let me finish with a few comments about this. So the existence of this function comes from our proof of the theorem that I just erased, which involves this construction of this polynomial. So the polynomial is defined in terms of some module, so some ZH module. I guess I don't have time to tell you what it is. I can tell you later if you're interested. And these metrics essentially come from certain eigenvectors of an associated matrix. So maybe I won't say too much more about that. What I do want to say, though, is that we got started thinking about this tree, T, because someone asked us, is there a more canonical way of defining this sort of polynomial? So I didn't mention it or say much about it, but this McMullen/Teichmuller polynomial. So we defined it in terms of this particular mapping torus, in terms of the particular choice of train track representatives. And it really only depends on the semiflow, but it does depend on the semiflow. So we were asked, is there a more natural polynomial that doesn't depend on any of those things? So Algom, Kafir, Hironaka, and Rafi, so they got around this sort of issue of dependence on x by taking the sort of minimal component of the polynomial. But we want some geometric way of building a polynomial that still gives us all the same information, but is independent of all these choices. And the idea is, there is such a polynomial. It comes from the tree T. It's defined similar to the way we define it for the mapping torus. So there's a module lurking around. And because this tree T depends only on the cohomology class, it depends only on the cone, you get some polynomial, therefore, that's sort of more natural. Now, the issue with that polynomial is it's impossible to calculate. Well, maybe not impossible, but so far we don't have a good method for computing it. So the polynomial that we defined and the other camp defined, they're really more tractable and just as useful. So it's not clear why you would want this other polynomial, except maybe to say that there's a geometric way of defining one. Okay, thanks.
So is theirs the same as yours?
Up to a factor. Yeah, up to a factor. So they take the minimal component, so and that has to be a factor of ours also. It's the one that sort of captures the stretch factor information.
Is there any hope of any kind of Bonner-Thurston kind of theorem in this context? So sort of, every free subgroup is either quasi-convex or a fiber in some sense, or is that?
Oh, it sounds like a question that I've talked to some people about before, and I don't know. Maybe people know the answer already. Yeah, I have to think about it more. Yeah, but possibly.
Okay, let's thank the speaker again, and let me just remind people that we have only 1 hour for lunch today, not 2. We start again at 1:30 this afternoon.